Extensometers are devices used in the measurement of length of objects. They have a high precision and are used in stress-strain measurements and also in tensile strength tests. There are basically two major types of extensometers based on their principle of operation. They are the contact extensometers and the non-contact extensometers. The contact extensometer is of various types, of which the clip-on extensometer is the most common. The non-contact extensometers are the laser extensometer and the video extensometer. The extensometer was invented by Charles Houston in 1879. Laser extensometer is used in elongation measurements or strain measurements on certain materials or specimen. The working principle behind the laser extensometer is that a laser beam is directed at the specimen, and the resultant reflections from the surface of the specimen are then received by a charge-coupled device, or CCD, whose information is then processed by a very complex software program or algorithm. So, video extensometers work by capturing continuous images of the specimen using a digital camera that's attached to a computer. The pixel distance can then be measured in real time and, mapped accurately against a calibration value to give a direct strain measurement of the specimen. With a good calibration value and some nice image processing data, you can actually achieve a resolution of even less than 1 micrometer. Extensometers are precision instruments used to measure the change in length or strain of a material when it's subjected to stress. They're, absolutely essential in materials testing and structural health monitoring. Here are 11 types of extensometers and their common uses. Mechanical extensometers. So these devices use mechanical components like levers and gears to measure the elongation or compression of a specimen directly. They're primarily used in laboratory settings for tensile tests and other static load testing of materials. So, electrical resistance strain gauges are these thin electrical devices that get bonded to surfaces, and they actually change their resistance as they deform. They're often employed in experimental stress analysis to measure strain in metals, composites, and, even concrete structures. Optical extensometers, on the other hand, use laser or optical systems to measure displacement without any physical contact. They rely on light interference patterns or laser triangulation. These are really ideal for non-contact measurements, making them especially useful for high-temperature applications or for sensitive materials where contact could actually affect the results. LVDT, or linear variable differential transformer extensometers, use magnetics to measure displacement changes. They're commonly used in precision applications like monitoring strain in civil engineering structures and in material testing machines. Hydraulic extensometers, they involve the use of hydraulic pressure to measure elongation or contraction in a specimen and are typically based on U-tube or piston designs. These devices are especially useful in applications that require high force or in geotechnical engineering, particularly for large-scale constructions. Digital extensometers are basically computerized versions of traditional extensometers. They provide digital readings and enhanced data logging capabilities, making them widely used in materials testing to provide data that can be easily analyzed and stored for research. Strain gauge extensometers utilize, strain gauges to measure deformation directly. When the material stretches, the strain gauge detects the change in electrical resistance. These are used in both laboratory and field applications to monitor deformations in structures like bridges and buildings. Bimetallic extensometers, these consist of two different metals that expand at different rates. when the temperature changes. This difference in expansion actually translates thermal expansion into measurable deformation. They're primarily used for thermal monitoring, especially in applications where fluctuations in temperature could, affect the integrity of materials. Fiber optic extensometers make use of fiber optic sensors to measure strain. They do this by detecting changes in light transmission through the fiber cable. These devices are particularly effective for monitoring soil structure interactions in civil engineering, and they're also used in real-time structural health monitoring of large infrastructure. Capacitive extensometers measure changes in capacitance that are caused by the movement of a sensing element in relation to a fixed plate. You'll often find them used in laboratory experiments, especially those involving material testing and structural deformation analysis. Coordinate measuring machines, or CMM extensometers, are systems that, utilize probe systems capable of measuring the exact positioning and displacement of an object in 3 dimensions. They're primarily used for high-precision measurements in manufacturing and quality control processes, especially in the aerospace and automotive industries. Each type of extensometer really serves unique applications, depending on the specific needs of the testing or monitoring environment. These range from simple laboratory tests all the way to complex structural analysis in civil engineering. In mining, the extensometer is used in the measurement of displacement on high walls. Geologists can then plot a graph of displacement against time to figure out if there is an imminent fracture or failure on the walls. Complicated wall failures can be determined by the use of laser beams or radar, which enables a 3-dimensional or even 4-dimensional analysis. Extensometers measure the extension, compression, or shear deformation of a test specimen during a materials test. They can provide key properties such as offset yield, total elongation, and complete stress-strain curves. Choosing the right one really depends on the material, the test standard, and the anticipated deformation. Many test standards actually set a specific gauge length requirement. Avoiding damage to a fragile specimen is also important, Swiveling knife edges on contact extensometers help reduce risk even for rough specimen surfaces. The right choice of extensometer for a test is dependent on several factors. The type of material and any test standard requirements will help focus your search, especially when considering different stiffness classes like elastomers versus metals, expected elongation, and whether you need to measure before or at yield. Other considerations include the clamping force required by a contact extensometer, specimen thickness, or the requirement for non-contact measurements. Very thin specimens, such as foils, may be sensitive to clamping forces, while very small wire specimens do not provide enough visible area for reliable non-contact measurements. Depending on the application, extensometers are available in both contact and non-contact models. In the case of contact, the 2 most common forms are probe or magnet and rod extensometers. A probe extensometer consists of a hollow flush PVC tube with a series of equal-length spaced-out magnets embedded inside a donut shape. A sprung leg is threaded over the PVC tube and pushed to its required depth by an insertion tool. When the sprung leg reaches its required length, the insertion tool is removed, and the instrument signals an audible signal indicating a load has been applied. Rod extensometers, on the other hand, consist of hydraulically operated anchors and connecting rods. These are connected to the measuring head by a flanged housing which is grouted concentric with the borehole. The measurement head itself consists of a hydraulically driven reference head and a connecting rod with a calibrated tip. During a test, the extension values are transferred to a machine controlling computer in tab delimited format making them easy to import into post-test analysis software such as MESPhysic. In addition, all results are displayed in real time on the video monitor in the test machine. Specimens that require the use of contact extensometers are first marked with measuring marks, which are either clipped, tacked, or glued onto the specimen surface. These measurement marks can become indistinct, fall off, or deform under load and are therefore a significant source of error. The latest generation of non-contact extensometers, such as the laser Extens from Zwick, eliminate this source of error by using the unique structure of a specimen surface as a fingerprint to generate virtual measurement marks. These measurement positions are illuminated with laser light and detected by a camera that is integrated into the testing system. This allows the measured strain to be converted into direct extension value. There are a number of different types of extensometer available, as explained at the beginning of this post. The choice will be influenced by the type of material and the test standards that must be met. In general, a class or required measurement accuracy will be specified in the test standard, and this should be taken into account when choosing an extensometer. Expected elongation before yield or at fracture is another important factor to consider when selecting an extensometer. So, there's a wide range of both contact and non-contact extensometers. A contacting extensometer, well, it attaches physically to the specimen and can be of the clip-on variety or, larger devices that attach directly to the test frame. Contacting extensometers are generally suitable for most tests. However, there are some exceptions that need to be taken into consideration. For example, very thin specimens such as foils can be sensitive to clamping forces, and small wire specimens may not provide enough visible area for reliable non-contact measurements. Similarly, the testing of very stiff or highly plastic materials often requires the use of a specially designed extensometer, which has been developed to resist these forces. Some of the main types of contact extensometers include sensor arm incremental and analog clip-ons and shear pin style devices. These are all capable of being used for tensile, compression and shear testing, as well as cyclic testing. They offer a range of gauge lengths to suit the various test requirements, and most will also work in both axial and transverse direction. As explained earlier, there are also several types of non-contact extensometers which use optical technology to measure the strain in a specimen. The main types of non-contact optical extensometers are based on a laser or an infrared beam, and they offer various options including a variety of measuring lengths, an integrated camera for localized deformation measurements, multiple measurement points along the specimen, and even a dedicated flexure extensometer, which can be used to test shear samples. Generally, it is best to select the highest specification extensometer that is within your budget, since it will give the best data quality and allow you to meet the most test standards without having to invest in more than one device. However, there are occasions when a more specialized or expensive extensometer will be vital for specific applications like torsion, biaxial, high temperature or cyclic fatigue, and so on. Many different types of extensometers exist to suit a wide variety of applications. When selecting an extensometer, it's important to consider the specific material and testing requirements of each application. For example, some materials, such as thin films, are best tested with non-contact instruments to avoid damage from contact. Additionally, some samples may need to be inspected at elevated temperatures and require non-contact extensometers to maintain measurement accuracy. When selecting an extensometer, it's also crucial to consider the ease of operation and ergonomics of the device. This is especially true if a lot of series testing is conducted, as it's important to minimize strain and fatigue on the operator's hands and arms. Some advanced models of extensometers include features such as swiveling knife edges that help to mitigate the risk of damage and improve user safety. It's also vital to determine how you will calibrate and verify the accuracy of your extensometer in advance. This can include electrical calibration, especially for strain-gauged extensometers, and, visual inspection for displacement measurements. Additionally, it's important to plan for preparing and storing your extensometer for use. Many models actually come with protective coverings and cases to ensure that they remain in good condition when not in use. Lastly, it's important to select an extensometer that will integrate with your testing machine. This will ensure that the data is transmitted accurately and the measurements can be displayed on screen for easy interpretation. Some advanced models of extensometer can also be operated using a computerized interface to make the setup and test process much faster and, more convenient. To select an ideal extensometer for your testing needs, you should start by determining the maximum extension or strain that you want to measure. This step will, allow you to select an extensometer that can handle the required loading conditions. Additionally, it's important to consider any other unique requirements, such as the need for a particular measuring range or specific temperature conditions. If necessary, it's also recommended to obtain a tech note that details the specifications of your testing standard. And finally, it's vital to check whether your equipment technicians have the training needed to operate and maintain an extensometer. The initial costs of purchasing a testing equipment like an extensometer may be substantial, but honestly, the real cost is the cost of maintaining it. The longer your test equipment sits idle, the more it is subjected to environmental conditions that can affect performance. These conditions include humidity, water exposure, and temperature extremes. In addition, jarring vibrations can damage or disturb the extensometer and cause, erroneous readings. This type of maintenance and protection is really an ongoing effort that requires everyone involved with the testing process. The first step in restoring an extensometer to calibration is to exercise it 2 to 3 times by running the rod from its initial position, or 0, through its full range of travel and back to its initial position. This process resets the sensor to its correct 0 position and also calibrates any electronics that might have been affected by hysteresis. When an extensometer is not being used, it should be stored in a protective case or other device to, prevent environmental effects from damaging the sensitive sensor. Moisture especially can damage the strain gauges used in many models of an extensometer. Short-term condensation normally does not cause permanent damage, but long periods of exposure can degrade the gauges and wires. If an extensometer must be exposed to moisture, it is recommended that the user dry it as soon as possible and store it in a container with desiccant. Optical extensometers can also suffer from out-of-plane motion, which causes an error in the measurement signal. To overcome this, scientists have proposed effective methods to compensate this error, but they have the drawback of requiring that the reference specimen is changed periodically during the testing procedure. For geotechnical applications, a fixed extensometer is often used to monitor settlement or heave between points without the use of a removable probe. This is done using a riser settlement rod that is either buried at the embankment, fill level, or grouted inside a borehole as a deep benchmark in a firm soil. Alternatively, an optical leveling extensometer can be used to monitor changes in surface elevation.